Welcome to this video. This is topic 12 of Edexcel International LFL Chemistry. This is the second topic of Unit 2. This is also topic 13 for Edexcel LFL Chemistry for those in the UK. So let's get started. So energetics, we will cover it in 4 pages. Page 1, page 2, page 3, page 4. That's it. So the key to really understand energetics is we have to know the definitions by heart, because they will ask us state what is meant by enthalpy change of this, that in exams for 1 or 2 marks. So we have to, when defining this, we have to keep in mind the molar quantities, standard state or not, and starting from what, ending to what, and also the process is exothermic or endothermic. We have to keep all of these things in mind. So let's get started. I have given 5 enthalpy changes here, but as I have said already, that Unit 2 and Unit 1 stuff can surely appear in Unit 4 or Unit 5 exams. So the other enthalpy changes, the enthalpy change of neutralization, the enthalpy change of combustion, those can also appear in exams. For combustion, the calorimetric investigations and neutralization, those enthalpy changes can also come in exams, but those are synoptic. But what is actually mentioned in the specification, what I mean to say is what is curated for Unit 4, I have included only those here, but do revise those Unit 2 stuff. Okay. So enthalpy change of atomization. It is the enthalpy change when 1 mole of gaseous atoms are formed from its elements in their standard states, and this is obviously endothermic, because we have got a chlorine molecule over here, and we have got half mole of a chlorine molecule, and if we break the covalent bond between the chlorine atoms, then we get 1 mole of this gaseous chlorine atom. So the first ionization energy, do make these corrections when you buy this note, only this correction. The first ionization energy, it is the energy required to remove 1 mole of electron from 1 mole of gaseous atom from 1 mole of gaseous unipositive ion. So removing 1 mole electron from 1 mole gaseous atom. You may ask me why we are not removing 1 mole electron from 1 mole of the element in its standard state, because sodium in its standard state would be a solid, but if we had done NaS and this, then we would not get ionization energy. What we would get instead would be the sum of atomization energy and ionization energy. That is why it is very important to understand this definition. This is the energy required to remove 1 mole electron from 1 mole gaseous atom, from 1 mole gaseous atom to form 1 mole gaseous unipositive ion. So this is obviously endothermic, because electrostatic forces of attraction between the electron in orbit and the nucleus has to be overcome to remove the electron. And first electron affinity, it is the enthalpy change when 1 mole of gaseous atom gains 1 mole of electron to form 1 mole uninegative gaseous ion. So if we have to input energy to remove an electron by overcoming electrostatic force of attraction with the nucleus, then we would definitely receive energy if we add an electron to an orbit to be in attraction with positively charged nucleus. We would receive energy. So energy will be released. This is obviously exothermic. Do memorize this. Atomization endothermic, ionization endothermic, first electron affinity exothermic. But the second electron affinity, third and fourth and so on are all endothermic, because energy is needed to overcome repulsion between negative ion and incoming electron. In first electron affinity, we had added 1 mole electron to 1 mole of gaseous atom. But in second electron affinity, we are adding electrons to already uninegative ions. Okay, we are adding electrons to already uninegative ions. So adding a negatively charged electron to a uninegative ion, there will be repulsion. Okay, so now the lattice energy. It is the enthalpy change when 1 mole of an ionic lattice is formed from its constituent gaseous ions. So constituent gaseous ions here forming 1 mole of ionic lattice, and this can be either endothermic or either exothermic. But these three are constant fixed, and so are these fixed. These and these, only these two can vary, depend. Now, lastly, the enthalpy change of formation. It is the enthalpy change when 1 mole of a compound, here 1 mole of a lattice, but here 1 mole of a compound. Compound can be covalent, compound can be ionic, any compound, but here 1 mole of an ionic lattice. So these are different definitions. So 1 mole of a ionic, so 1 mole of a compound is formed from its elements. Constituent gaseous ions, elements, different thing. Under standard conditions in their standard states. So sodium, standard state solid, half mole chlorine gas, standard state gaseous, forming 1 mole sodium chloride ionic lattice. and this formation enthalpy in this case is endothermic, sorry, exothermic. So if this is exothermic, this is thermodynamically feasible. This will occur at room temperature. We do not have to put in energy for them to react from this. This will automatically, this will naturally occur. Formation of sodium chloride or table salt will naturally occur because this is exothermic. Now the Born-Haber cycle. This was included in AS Unit 1 in the older specification, but it got removed from the new specification and got moved to Unit 4. So this is really important. The types of question you will be asked in exams will be, you will be asked to construct this. Obviously, you will be given these values, and I'll tell you some tricks as well. Then this, not much. Okay, so this is the time you will understand what Born-Haber cycles are completely. Because in AS, you got them in your question papers, older question papers, but you were not taught them in class. So now you'll be taught them. So the whole idea is the formation of an ionic compound isn't a single one-step process. No, no, no. It is not taking place in a single step. Sodium chloride is not taking place in this single step. It includes many steps, such as first we have to turn the sodium solid into gaseous atoms, gaseous chlorine molecules into gaseous chlorine atoms, removing electron from sodium, ionization of sodium, electron affinity of chlorine, then bringing the oppositely charged ions to form an ionic lattice. All of these to form this. Got you. So the energy released when the lattice is formed is, so the lattice energy we are talking about is more than enough to compensate for the endothermic changes such as atomization and ionization. Diagram below is Born-Haber cycle of calcium chloride. So I'll tell you some tricks and tips that will be helpful to you for being able to draw this in exams from scratch. So what you really must keep in mind and using your intellect is that you must be able to identify which of these processes are endothermic and which of these processes are exothermic. So as we read above, atomization is always endothermic, atomization is always endothermic, ionization always endothermic, but first electron affinity is exothermic, and lattice energy exothermic because it is forming exothermic. And formation, these two could depend. So how you will start? Let's use our knowledge of vectors. This is our starting point, this is our finishing point. We can go from here to here in a single line, but we can also go from here to here like this. 1, 2, 3. So my advice is you always draw a horizontal line. Label this energy axis, y axis, x axis later on, but you always draw a horizontal line, and on the horizontal line, the first thing that you should be doing is writing the elements in their standard states. So first draw a horizontal line, then write the elements in their standard states before doing anything. Once you have done that, first what you do is you do atomization of one element, then you do atomization of another element, then you do ionization of the metal. If two ionizations are required, then do that, and then you do the electron affinities. After you have gone from here to here, you have formed oppositely charged ions, and do make sure to draw electrons, writing electrons where required. And after you have reached this far, from here to here, all you have to do is draw a downward arrow, draw a downward arrow, and this will be the lattice energy, and this will be the lattice energy, and this is the formation energy. So this is how you draw a Born-Haber cycle easily. You will be obviously given the data values for being able to draw this, and these must not be to scale. You're not required to draw this to scale. These can be rough hand diagrams. But one thing to really keep an eye out for is that we got in standard state, we got one mole of chlorine. So if we have to do atomization of chlorine, atomization means forming 1 mole of gaseous atom, 1 mole of gaseous atom. But here we would form 2 mole of gaseous chlorine atom. Therefore, atomization of chlorine multiply by 2. Likewise, electron affinity of chlorine multiply by 2. Many students forget to multiply by 2, and then they get wrong answers in exams. So don't make that rookie mistake. So rearranging for starting from here, finishing here. Starting here, this was our vector start, finish. Start, finish. So rearranging this, blah, 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 then rearranging for lattice energy, we find out the lattice energy or lattice enthalpy. So now You have obviously read this in AS, the polarization, bonding continuum, purely ionic, purely covalent, then between ionic covalent, those stuff. But this is more in details because this is A2 Unit 4. So theoretical versus experimental lattice enthalpy. The Born-Haber lattice enthalpy is the experimental one. The one we are calculating here is the experimental one. The theoretical one can be found if the ionic radii and the arrangement of the ions in the lattice are known. How? Easy. Let's relate this. Le, Q, Q, R, R. So if these values and these values are known, then the theoretical can be found out, and experimental is found out like this. So difference between theoretical and experimental, that is enthalpy values, indicates that the ionic compound isn't purely or isn't 100% ionic. So it has some extent of covalency, and so you already know this. But what you may not know is when an ionic compound has some extent of covalency, it tends towards giant covalent structure, not simple molecular covalent, but rather giant covalent. So the experimental values are larger than theoretically assumed 100% ionic values. So let's say we got an ionic compound and we are calculating its theoretical value using this, and we also find out our theoretical value using this. Let our theoretical be x, and we find out the experimental Born-Haber value like this. That will be y. So the question is, which will be the larger value? This will be the larger value. Y will be larger. The Born-Haber, the experimental value is larger. Why? I'm telling you why. Give me a minute. Okay. But firstly, factors affecting extent of covalency, polarization, AS level stuff, I won't go in details. Large charge, small size. Larger the charge density of cation, there is some background noise. Some blabbering noise, bad noise. Ignore that. So large charge and small size, large charge density of cation, greater the polarizing power. Large size and large charge. So in case of anions, we are not having a large charge density anion. We both have large charge and large size. 1 minute. So we are back. The greater the difference between theoretical and experimental, that is energy values, the greater the extent of covalency. Simple as that, but maybe a common marking point that could be missed. So this is a typical exam question. This can come for 3 marks to 6 marks, but commonly comes for 4 marks. I have included all of these points from mark scheme, so feel free to memorize these as they are given. So the cation has a high enough charge density, or you could say the cation has a high enough charge and a small enough ionic radii instead of this. So cation has high polarizing power. Anion has high charge and high radius. So anion is very polarizable, or anion is sufficiently polarizable. Cation distorts the electron cloud of the anion, resulting in polarization. Distorted electron cloud. So you remember those diagrams from back in AS. So polarization happens, and polarization leads to extent of covalency because there was some sort of overlap of electron cloud. So this represented a covalent bond. So leads to some extent of covalency. So experimental lattice energy is more exothermic than expected than the theoretical. And we had above said that y was greater than x. What I meant was uh, experimental was more exothermic than theoretical. Why? Because more energy is required to break more ionic and more covalent bonds. Because there was some overlap. There was some overlapping. There was some covalent bonds formed. So and these covalent bonds formed were in the form of giant covalent structure. So now we have to break both ionic bonds and covalent bonds. We no longer have to break only ionic bonds. Therefore, more energy is required. Therefore, Y is more exothermic. Therefore, theoretical is less exothermic and experimental is more exothermic. Experimental, more exothermic. Now the formula of ionic compounds. So far, this quite commonly appears in exam, as does this, so does this. But this is something that has not appeared in exams to be called a common question. So just because this is not common, so do give more priority to this subtopic. Formula of Ionic Compounds. So ask yourself the question: why is magnesium chloride MgCl2? Why is it not MgCl or MgCl3? Does the answer lie in noble gas configurations? Does it lie in how many electrons can you lose when you have an octet, whether you have an octet or not? No, no, no. The answer does not lie in octet formation. The answer lies in enthalpy. So the formation enthalpy of MgCl2 is most exothermic out of the three. So MgCl2 is the most stable. So these are the formation enthalpies. This is exothermic, this is exothermic, this is endothermic. So, when we have mixed magnesium and chlorine, the greatest quantity of compound we will receive will be MgCl2. Some of this will be received because this is still exothermic, but majority will be MgCl2, and this will not be present unless we give energy externally. So the reason for this being endothermic is this: the third ionization energy of magnesium is very high, so it's not compensated by the lattice energy of magnesium chloride. Lattice energy is exothermic and ionization energy is endothermic. So the lattice energy of MgCl3 is not releasing enough energy to provide energy for removal of the third electron, so making formation of enthalpy change of MgCl3 highly endothermic. You just rearrange this diagram. Le, this blah blah blah. This will come to be positive. Positive for MgCl3. Now solubility. You have read about this back in unit 2, ion dipole attractions, hydration, but unit 4 we will go more in details. So the process of solubility or the process of dissolving an ionic compound is simply that lattice dissociation, opposite of lattice energy, takes place at first, forming ions, and the ions are surrounded by water molecules and hydrated. Therefore, hydration enthalpy occurs, which is exothermic, and this is endothermic. So, if hydration enthalpy is exothermic enough, it will compensate for endothermic lattice dissociation enthalpy. Hence, ionic solid becomes soluble. Why it becomes soluble? Because of this. This is positive. This is negative. If hydration enthalpy is exothermic enough, then enthalpy change of solution will be exothermic. If enthalpy change of solution is exothermic, then solution is happening, dissolving is happening, solubility is happening, solubility is feasible. Therefore, ionic compound is soluble. As easy as that. I have included these diagrams here for very good reasons, because one misconception must be clear. Many teachers, many desi teachers, just for simplicity, like to say that when you dissolve an ionic compound in, let's say, a beaker of water, first the ionic compounds, first it breaks and then it gets hydrated. That is false. That is not accurate. Rather, what happens is this hydration enthalpy and lattice dissociation enthalpy occurs simultaneously, occurs at the same time. Okay. So you may be asked to draw this in exams. This has come in exams, so has this, but this has never come in exams. But I found this from the George Fisher book. And they like to give things, they like to come up with things from the George Fisher book. Okay, now for the definitions. Lattice dissociation enthalpy, negative, give me a minute. It is the energy required to split 1 mole of ionic lattice into its constituent gaseous ions. Lattice energy it is the energy required to, it is the energy released when 1 mole of an ionic lattice is formed from its constituent gaseous ions. But here, opposite, splitting 1 mole ionic lattice into constituent gaseous ions. Therefore, because lattice dissociation enthalpy is the opposite of lattice enthalpy, that is why we give a negative sign in front. So, hydration enthalpy. It is the enthalpy change when 1 mole of gaseous ion is dissolved in sufficient solvent to give an infinitely dilute solution. I'll make you understand this very well. So, let's say we have got some molar quantities of gaseous ions in a solution in a beaker of water. And if we continue adding water, there will be a point when no more hydration takes place. All of the ions have been hydrated. So after that point, if we add any more water, then no more hydration is taking place. So no more energy is being released. So we have found a diluted solution, infinitely diluted solution, because of addition of sufficient solvent. So that is why including these phrases, these parts in your definition is very crucial. Then enthalpy change of solution. It is the enthalpy change when 1 mole of ionic solid is dissolved in sufficient solvent. Here 1 mole ionic solid, but here 1 mole of gaseous ion. Different thing. to give an infinitely direct solution, but the explanation is the same. So you will be asked to you will be asked about this in both of these in MCQs. But um, for example, you will be given equations like this. Let's say sodium gas becomes Na plus aqueous. So this is hydration enthalpy of sodium ion. Perfectly fine. But you will not be told that in the MCQ you are being asked about hydration enthalpy. Rather, what you will be given is you will be given two equations. Let's say for sodium, an equation like this for sodium. Listen to me carefully. And an equation like this for barium. And you will be asked in MCQs whether the enthalpy change is enthalpy change. They will say enthalpy change, but they will not mention what enthalpy change of what. So enthalpy change is option A, more exothermic, less exothermic, more endothermic, less endothermic, or the same. They will give options like this. So how will you understand what enthalpy change is this? If you don't understand what enthalpy change is happening, just by if you are not able to come up with the enthalpy change just by deducing an equation, or if you cannot deduce the equation of enthalpy change, then you will not be able to apply these factors affecting these enthalpy changes, and you will not be able to answer the MCQs. So do be able to do that. And this can be represented as Hess law cycle, um, unit 2 stuff, similarly like this, starting from solid 1, 2, ending in solution, simple vector. Start, end, treat it like that. So I'm not going into it. You can understand this. So factors affecting lattice energy and hydration enthalpy. For lattice energy, magnitude of charge, greater the magnitude of charge. Wait a minute. So for lattice energy, greater the magnitude of charge, more exothermic the lattice energy. Smaller the sum of ionic radii, smaller its sum, greater the or more exothermic the lattice energy. Arrangement of ions, smaller ions pack more strongly. And the extent of covalency. Greater the extent of covalency, more exothermic the lattice energy. And one thing you should understand is, if the magnitude of charge is greater, the lattice energy is more exothermic. But what about the lattice dissociation energy? If the lattice energy is more exothermic for an increase in charge, the lattice dissociation energy will also be more endothermic. I'll explain that when we go down. So then hydration enthalpy, factors affecting hydration enthalpy. Magnitude of charge. The greater the magnitude of charge, the more the attraction for the water molecules, the more exothermic the hydration enthalpy. The radius of ion. The smaller the radius of ion, the more it can be surrounded by more water molecules, therefore more exothermic the hydration enthalpy. Role of entropy in solubility. Let's see how much time. They are okay. I'll have to go fast. Role of entropy in solubility. This will be for the next video. Next video on entropy. I will link energetics and entropy together. So now this is also mentioned in the specification, but all of these follows periodicity. So going down the group, what happens to ionization energy, what happens to ionic radius increases, those stuff you should revise those from unit 1, easy stuff. So let's continue. But first let me drag this. Hey, foul. Really pissed. All right. Solubility of group 2 hydroxide. So down the group, charge remains the same, obviously, because they are all group 2. So they all have 2 plus 2 charge. But ionic radius increases. Yes, ionic radius increases. It does increase. So if ionic radius increases, then sum of ionic radius increases and lattice energy becomes less exothermic. So less energy will be released on formation of the lattice, and less energy will be required likewise to break that lattice. So what will happen to the lattice dissociation energy? The lattice dissociation energy will become less endothermic, meaning so hydration enthalpy also becomes less exothermic because ionic radii increasing. So the trend was here. the hydration enthalpy becoming less and less exothermic. But the change in, another thing I must bring is this. Okay. But the change in hydration, um, but the change in hydration enthalpy is less than that in lattice dissociation enthalpy, negative sign. So enthalpy change of solution becomes more exothermic down the group. Becomes more exothermic, so solubility, enthalpy change of solution, more exothermic down the group, so solubility increases down the group. Let me make sense of it. So this is positive and this is negative. So uh, if this becomes less positive, this becomes less positive, this becomes less negative. But change in this is much less, and change in this is much more. So this becomes much less positive. Sorry, this becomes much less positive, and this becomes uh, the decrease in negativity is much less. How can I explain this better? Wait a minute. Okay, so we are back with a better explanation. What I tried to say was, English isn't my first language anyway, but what I was trying to say was that this definitely, that is dissociation and enthalpy definitely becomes less endothermic. The positivity of this decreases, it becomes more negative. This becomes more negative, and this becomes less negative. All right, but the decrease in its negativity is much less. So as a result, the net effect is that negativity of enthalpy change of solution increases. Now for group 2 sulfates, down the group 2, charge remains same absolutely, radius increases absolutely, but sulfate ion is already much larger in radii compared to any group 2 ion, because sulfate ion consists of, it is a polyatomic ion. So change in sum of ionic radii is very small. Change in sum of ionic radii is very small. This changes, but this change is very small. So lattice energy does not change significantly, and lattice dissociation energy also does not change significantly. But hydration enthalpy still decreases and becomes less exothermic as ionic radii increases down the group of the cations. So if we erase this remains almost constant, while this decreases, becomes less negative. Negativity decreases. So negativity of enthalpy change of solution also decreases. So enthalpy change of solution becomes less exothermic down the group 2, hence solubility decreases down the group 2 of group 2 metal sulfates. For hydroxides, group 2 metal hydroxide solubility increases. For group 2 metal sulfates, solubility decreases. That's it. End of energetics. In the next video, we will be looking at entropy. This is also really small, 3 pages entropy, and I have drawn in large handwriting. It's really an interesting topic and the easiest topic. Then, so see you in the next video. And the note for energetics, really good note, it will be in the description, and it is absolutely free.